Welcome to lesson 62, variation problems. I thought it might be a good idea to put this lesson after we just got through doing rational exponents, fraction exponents, exponents that can be things like 2/3, or if you put it to decimal form, exponents that can be things like 0.6 or whatever, because this shows you such things actually showing up. Maybe you're not right away, but towards the end of this lesson you're going to see some funky exponents start showing up. But nonetheless, it's good to fit this in somewhere in the course, because variation, it turns out, is like a lingo, a jargon, a language, something like that you will see in a lot of your science books and technical technology type books and stuff like that. It's a language that gets used, and you just want to understand what are they saying, what are they talking about. So there are, I believe, 4 types of variation that we're going to look at. 5 examples for 4 types. The first type is something called direct variation. Okay, so what is this? Here's an example of direct variation. Biff is getting 200 eggs per week from his 40 chickens. Okay. Eggs are worth a lot now too, aren't they? Anyway, assuming that the number of eggs is directly proportional to the number of chickens, and this is what I mean by the language of variation right there. These kind of phrases where they say blah is directly proportional to blah, and that could be inversely proportional. It could be all kinds of stuff that we'll see those in this lesson. But this is the kind of language that you will see in your various science books and technology books and stuff like that. So anyway, continuing. Assuming that the number of eggs is directly proportional to the number of chickens, what is the governing law for Biff's egg farm? Okay, now at the moment that's going to seem like a mysterious question, but let me show you how it goes. You take this sentence, assuming that, you take this sentence, number of eggs is. Let's use E to stand for the number of eggs. Is means equals. So far, so good? Okay, number of eggs is. Now, when they say directly proportional to, what they mean is there's some constant that you multiply by. There's a constant of proportionality is what they call it. The number of eggs is K times something. Times what? Keep reading. Times the number of chickens. So let's use C to stand for the number of chickens. And might not be a bad idea to label this. So capital C is the number of chickens. Capital E is the number of eggs that you get from these chickens. And the K is called our constant of proportionality. And this thing that we just wrote, this little formula type thing, is what we mean when we say what is the governing law. What's the formula? What formula can we use and apply to analyzing Biff's egg farm? We can use this formula right here to analyze Biff's egg farm. Now the formula is not that big, fortunately. It's just a nice little E equals K times C. But you have to be able to interpret that language in order to write down that formula. So, okay, we've got the formula. What can we do with the formula? We can go on to this. Evaluate the constant of proportion. We can figure out what the K is. What's the K? Well, see, the thing is, up here we have some information that we can use. This information says that when the number of eggs, and maybe I'll just kind of put it right here, when the number of eggs is 200, we get, or I guess we don't get, we have 40 chickens. When the number of eggs is 200, we get 40 chickens. I guess it's maybe more natural to say when we have 40 chickens, we get 200 eggs, but in terms of the math formula, you can say it either way. But anyway, we know what the E is. They told us 200 eggs. We know what the C is, 40. They told us 40 chickens. Now we can solve for the K. So you gotta basically divide both sides by 40, right? Divide both sides by 40 and you quickly come up with K equals 5. And if you want, you could put units on this, 5 eggs per chickens. I'm not going to worry too much about following the units around in this lesson. But that's what it is, 5 eggs per chicken. Every chicken gives you 5 eggs per week or whatever this is. Now, why go through this whole 5, get a constant of proportionality k thing? Well, this is why we have these governing laws. We say, look, it doesn't matter which egg farm you go to, if it's Biff's, if it's Sally's, if it's in Minnesota, if it's in Florida, if it's this breed of chicken, if it's that breed of chicken, according to different farms in different places with different chickens during different times of the year, maybe, whatever. There's all kinds of variables, right? The K is going to bounce around. The K will bounce around. Sometimes you'll get 4 eggs per week. Sometimes you'll get 3 eggs per week. You might get 8 eggs per week, whatever, from each chicken, whatever. The K bounces around. So what you have is you have that, generally speaking, the equation is going to look some kind of there's going to be a number here that we're calling K, or constant of proportionality, that you can take the chickens, multiply it by that number to figure out your number of eggs, okay? That part will always be true, and that's why we call it a governing law. You can always write an equation that says E equals KC. So again, the value of K can bounce around from farm to farm and so on, from breed of chicken to breed of chicken, whatever. The K can bounce around. But what you can do is you can say, look, this is what I got going on right now. I'm getting 200 eggs from my 40 chickens. That's what I got going on right now. So for my little operation here, if this is Biff talking here, right? My little operation here, I can say that my number of eggs is 5 times my number of chickens, okay? So that's the formula I can now use to answer such questions as, hey, I want 750 eggs. So how many chickens do I need? Put 750 in for the eggs, solve for the number of chickens. We have to divide both sides by 5 here. So what you'll get is, let's see, 750 divided by 5. What is that? 150. Going to need 150 chickens under the present conditions of whatever your chickens are and whatever you're feeding them and whatever else. Okay, so you will need 500 chickens. Cool. This is just a sketch a graph of this situation. Well, whenever we say direct proportionality, what we have going on in the background really is a straight line graph that starts at the origin and goes like this. This is a line that goes up by K over by 1. It's got a slope of K. It's actually the slope of the line. So what did we have? We had eggs along the y-axis, chickens along the x-axis. It looks like this. This is just to give you something else to link it to. It's all of these things, no matter the direct proportion is always going to be a straight line going through the origin. So Biff's farm right now had 5 eggs for every chicken, right? There might be another farm somewhere else that has 8 eggs for every chicken. Maybe on Biff's farm, if he switches the breed of chicken, he might only get 2 eggs for every 1 chicken, whatever. So you get like a family of curves here, but they're all share this characteristic that you can write an equation, E equals some number times C. All of these lines have that kind of equation, E equals K times C. This is what's going on behind the scenes when people say this. When they say the number of eggs is directly proportional to the number of chickens, all of that is happening in the background. All of that is sort of what's going on, I guess. So anyway, I'm elaborating quite a bit on this thing. I think I can probably do some more examples where we maybe just get her done, right? So let's go to example 2. Well, this is a different kind of variation, actually. It's called inverse, but that only changes the problem a little bit. So how does it change it? Well, let's see. First of all, this is a situation. Sally assigns a crew of 8. They get the job done in 12 hours. Okay, that's nice. That's just information, I guess. Where's the law? Here it is. Assuming that the size of the work crew is inversely proportional to the completion time. What is the governing law of this operation? The size of the work crew. You need to come up with a letter or something, a variable. How about N for how many people are working or something? So size of the work crew. What I'm doing is I'm taking the sentence that I just circled and I'm turning it into an equation. The size of the work crew is, well, that means equals. Now, Inversely proportional to means not k times, like we did in the previous problem, but k over. And that's the big difference with inversely proportional. It's not k times, it's k over. Inversely proportional to what now? The completion time. How about we use t to stand for time? So t is the, not a bad idea to label our things. Time it takes, time to do the job. And n is the size of the work crew. So this sentence right here is telling us that this is the formula we should use when we're analyzing this whatever her situation is, whatever this job is, painting a fence, building a foundation, I don't know what they're doing. But for this job, for Sally's crew, this formula applies. We can use this kind of a formula to analyze her crew. Now, let's go to the next part. Evaluate the constant of proportionality k, that means solve for k. Find the k for Sally's operation. So this is why we need this information up front. It's like that's going to help us figure out what k equals. So they're saying when we had a crew of 8, okay, I think I'll change colors now. When we had a crew of 8, I don't know what k is. When we had a crew of 8, it got done in 12 hours. So we knew the n, we knew the t. Now we can solve for the k. So notice you multiply both sides by 12. Basically, k is 96. K is 96. And so that means for Sally's operation, n equals 96 over t. I solved for the k. It's 96. So I can change the n. I can change the t. The k is going to stay at 96. And this equation, using k equals 96, this equation is going to tell me, hey, if you change the t to this, it's going to change the n to that. If you change the n to that, it's going to change the t to this, and so on. So this equation now represents Sally's workforce, whatever it is that she's doing here. We can now use this to do analyses, answer questions, things like that. She assigns a crew of 12, so how long will that take? Crew of 12, huh? Crew of 12 means we're going to set the crew to 12, and the question is, how long will it take? T equals what? Well, if you just kind of put the 12 there and you say 96 over t over here, you got to solve for t. Multiply both sides by t, and you got this. Divide both sides by 12, and you got this. And so that comes out to 8 hours. So it's going to take 8 hours. Which, by the way, is kind of interesting, isn't it? If you think about it, a crew of 8 took 12 hours. A crew of 12 took 8 hours. Okay, it turns out that 8 times 12 comes out to 96. And so however you set the size of the crew, it's always going to be the case. The size of the crew times the number of hours is going to be 96. In the old days, we used to call those man hours. I don't know what you call them nowadays. Staff hours or something. Something like that. I don't know. Okay, so the inversely proportional, what was the net effect? It was up here. It was k over instead of k times. That was the big difference. So quick review. Example 1, direct variation, it was k times. Inverse variation, it was k over. Well, what else can happen? So I said there were 4 things that could happen, right? So what else can happen? You've got the direct, you've got the inverse, you've got the k times, you've got the k over. What's this? This is something called joint variation. According to Newton's law of cooling, okay, the heat loss from a wall of your house is jointly proportional to the wall's area and the temperature difference between the indoors and the outdoors. So there's the sentence that we need to translate into a formula, into a law, if you will. So let's see. The heat loss from a wall of your house. What symbol do you want to use for heat loss? How about H? Sound good? Heat loss is. Now, when they say jointly proportional, is it going to be k times? Is it going to be k over? What's it going to be? It's going to be k times again. So it's kind of like direct variation. It's just that we got more than one thing coming after the k. It's jointly proportional to the wall's area. How about we use an A for area? And the temperature difference. temperature difference. I'm going to put like a T diff or something to say temperature difference between the indoors and the outdoors. Okay, so the formula is a little bit bigger because we've got, oops, that's not what I wanted to do. We've got our H here, we've got our K here, and then we've got our A here, but we've also got another thing over here, okay? That's all that joint variation means, is that you're just going to kind of have a big long line of stuff all kind of slummed together like that. So there's our law. That's part A. We wrote, that is actually called Newton's law of cooling. Now, if you lose 320 BTUs per hour, that would be your heat loss. So we're going to start plugging these numbers in. 320 BTUs per hour. Okay, through a wall with 160 square feet, that would be the area, 160 square feet. When it's, okay, now we got 40 degrees outside, 70 degrees inside. Now what I want here is I want the temperature difference. So what's the difference between 40 and 70? It's 30 degrees is the difference between 40 and 70, right? It's like you're trying to heat your house up by 30 degrees. Because if you turn the heat off, your house is going to end up at 40 degrees eventually. But you're trying to get it back up to 70. So you're trying to heat it up by 30 degrees. That's why the temperature difference is important. So anyway, that's that. There's the K. Okay, I guess it's time to solve here, huh? We can now solve. So depending how you want to do this, you could just kind of multiply the 30 times the 160 right away, which will give you this, 4,800. Then you would divide both sides by the 4,800 like this. And so you end up with K equals, and I'm a little old-fashioned, so I'll just do the old cancel some zeros here. 32 and 48 can both be divided by 2. So that would be 16 over, that's not 48, that's 480. That would be 16 over 240. I'm going to divide by 2, that's 8 over 120. I'm going to divide by 2, that's 4 over 60. I'm going to divide by 2, that's 2 over 30. I'm going to divide by 2, that's 1 over 15. K is 1/15. Just because this is a video and it's going to get posted, let me get my calculator out and double check that. So 320 divided by 4,800 is 1/15. Good, I got it right. K is 1/15. So what can we do with that K? Well, we can finish writing the formula. So for this house or whatever, at this climate and this whatever, the heat is, that's a fraction, 1/15. I can just put it there. Times the area times the temperature difference. This formula applies to our house. Now we can use that formula to talk about the house some more. Like up here, what's it say? Let's get a different color. Up here it says, okay, what is the expected heat loss? Find the H when it's 20 below outside. Okay, find the H. We're going to find the H. So when it's, how cold? 20 below. Okay, so -20, you want to heat it up to 70, right? That's a temperature difference of 90 degrees. Holy cow. So you're going to heat your house up by 90 degrees. Yeah, that'll take a strong furnace to do that. What's the area of our walls again? Well, actually it says right here, use a total surface area. We're going to throw the roof in, I guess. Walls in the roof of 10,000 square feet. 10,000 square feet. And so here, I suppose you could just grab out your calculator and do this, right? So on my calculator, how would I do this? I would say 10,000 times 90 divide by 15 equals, and I'm getting 60,000. Now, what are the units of that H? It would be the same as the units that we had before, which was BTUs per hour. BTU is a British thermal unit. BTUs per hour. This is an old-fashioned measure, still used, of course, but it's an old-fashioned measure for heat loss. Nowadays, we use watts per square meters if we're engineers, but who cares? So it's BTUs per hour, which means if you want to buy a furnace for this house, you want to say, hey, give me a furnace that can do 60,000 BTUs per hour. That way I can heat my house when it's 20 below, you know. So this is practical stuff. If you go into HVAC, you'll be sizing furnaces. You'll be using this Newton's law of cooling and stuff like that. Okay, so in terms of math class, let's review the basic idea. The basic idea was right here. Actually, let me erase a lot of this stuff so it'll be clearer to see. Get out of here, get out of here, get out of here, get out of here. Okay, right here. Heat loss from a wall is jointly proportional to the area and temperature difference. That you can interpret that directly. Heat loss is my H. Jointly proportional to is telling me K times a bunch of stuff. What bunch of stuff? The wall's area and the temperature difference. So it's a language that you can interpret and write directly as a nice little formula. And then you can use the formula for whatever houses, wherever, and so on. You use the house to solve for that house's K. You use data from the house, I should say. Like this house, we had this much heat loss through this wall when it was this much of a temperature difference. That tells us what K is for the house, which kind of amounts to what kind of insulation have you got in your walls anyway. That's what that amounts to, the K. But once you've got your K, you can say, okay, so if I change the temperature or whatever, what size furnace will I need? Ooh, looks like we got, yeah, that's why we have 5 examples, 4 types. We have a second example of a jointly. This is another one of those jointly variations. So this is kind of interesting stuff, really, especially for those of you who might go into civil engineering or anything like that. So there's the flow of water over the top of a dam, which they sometimes call a weir. The flow of water over the top of a dam varies jointly with the width of the dam and see, that's what I meant by fraction exponents. The 3/2 power of height of water measured above the dam. What is that talking about? Well, I can draw a nice little picture here. Pretend that's a dam. Okay, so that's like a dam. When they say, usually with a dam, you think in terms of you want to block the river so it doesn't go by. But if you go to like downtown Minneapolis, you go to the Lock-in Dam, you'll see that there's a sort of a dam type thing where the water is actually flowing over the top. And maybe I should try to make an end on view. The water is flowing over the top of this thing. They actually do that so they can measure the flow rate of the river. You know, the Army Corps of Engineers, they like to keep track of this stuff. What's the flow down the Mississippi? And take historical records and all this stuff. Anyway, it turns out this flow rate depends on, reading back here, the flow rate depends on the width of the dam. I guess that makes sense. I guess we'll call that W, the width of the dam. But also, 3/2 power of, okay, height of water measured above the dam. So that would be this here. How high is that? The water's flowing over the top of the dam. Well, how high is that? Do you get 2 inches of water flowing over the top? You got 2 feet of water flowing over the top? What is it? Okay, so those are the 2 things that matter to get your flow rate. So, okay, let's interpret this formula now. The flow rate of water, we need a letter. How about F? Flow rate of water over the top of a dam, which civil engineers call a weir, varies jointly with, okay, that's going to be another one of those K times multiple things here. The width of the dam, we'll call that W for width, and the 3/2 power of, now be careful here. 3/2 power of what? 3/2 power of the height of water. Okay, so that's the height of water. We'll use H to be the height of water, but it's not the height of water. It's the 3/2 power of that, which means you've got an exponent on here, a 3/2 exponent. So it's a little more funky, So there's our formula for the weir. So this'll work. So, okay, let's start analyzing the Mississippi River or something here. What do we got? So the next thing it says is write the governing law. I guess we just did that. Part B, we've got 100 gallons per minute. That would be the flow. Flowing over the top of a 10-foot wide dam. That would be the W. When the water measures 3 inches above the top of the dam. Okay, so that 3 goes there. Don't forget there's a 3/2 power. So that's what we got. And then what flow rate would we expect if we change things? Okay, so before we change things, we should figure out what the K is. Now this is gallons per minute. This was feet and this was inches. Now, all that really matters is that when I keep using this formula, I always use feet here. I always use inches here, I always have gallons per minute here. As long as you keep the units the same every time you use the formula, you don't have to really worry about the units. But I'll make that notation here that we do want to keep these units as feet, inches, and gallons per minute. So anyway, we have to solve for the K here. How are you going to do that? Well, I suppose one thing you could do is you could grab out your calculator and you could multiply 10 times, turn it on first, 10 times, and then you have to hit 3 and then use the exponent button to raise it to the, and you could write 3/2 or you could just say 1.5. Your calculator understands 1.5 exponent. So 10 times 3 to the 1.5. So this is what I'm entering on my calculator right now. This. And what am I getting? I'm getting 51 point something like 9615. Okay, cool. So you see that basically what I got to do now is divide both sides of this equation by the 51.9615. I would suggest that you not copy the 51.965 on your paper or anything, but just you have that number staring in front of you on your calculator right now. So all you really have to do is go 100, divide by, and there's usually a little ANS button that says give me back my previous answer. So if I go 100 divide by answer, it will tell me 1.9245. And I do like to carry decimal places when I'm doing this variation technical type stuff. So that's our K. Okay, so that K applies to whatever river this is, you know, whatever temperature the river's at. I mean, whatever variables are involved, this K is working for our local situation here. Now, we're going to change things a little bit because it says, or it asks, what do we expect for a 20-foot wide dam when the water is 5 inches? Okay, so we're changing the W, we're changing the H. What's going to be the new flow? So first of all, I guess I could have said right here that since I know the K, I can take this law here and I can rewrite it using that value for K. And I might as well just write that as 1.5. Okay, so this is the formula we're going to use. And they said change the W to, I want to say 20. Let me double check. Yep. And the height is going to be 5 inches. And remember what I was saying before, as long as I keep this feet and I keep this inches, I'm good. This will be gallons per minute. So it's really just button pushing now, right? So the flow rate is 1.9245, just to write it out. I'm going to plug in a 20 for the W. We're going to plug in a 5 for the H, but make sure you use your exponent button, raise it to the 1.5 power, and what am I getting here? 1.9245 times 20 times 5 raised to the 1.5 equals. And make sure that you push, when you push your buttons, make sure they come out the same. 430, and I could say 0.3 or something, gallons per minute. So what did we originally have? We had 100 gallons per minute for a 10-foot wide dam. We made it twice as wide. You'd expect 200 gallons per minute, right? But we're getting 400 gallons per minute. Why? Because we also increased the height from 3 to 5 inches. So yeah, we did expect more water to be flowing over that thing. So there it is, 430. One more example. This one has a new name. It's called combined variation, which is kind of like the joint variation in the sense that we're going to have more than one thing to tack onto our K. What's different is that it's going to sort of, well, it says it right here. It's going to combine directly and inversely together. So remember, directly meant times and inversely meant K over. So some stuff's going to go on top, some stuff's going to go on the bottom. So here we go. Let's do this. It says Newton's law of gravity states. Okay, cool. That force of gravitational attraction between two bodies varies directly with, okay, so the force of gravitational attraction, let's use F for that, varies directly with means K times, remember directly means times, the masses of the two bodies, so not just one mass, but two masses of two bodies. I guess I'll say mass of body 1 and mass of body 2. So directly with the masses of two bodies. And inversely with, okay, that's where you get your fraction bar going. Inversely with means this stuff goes underneath. And be careful again. It says square of the distance between them. So I can use d for the distance between them, but it's not just the distance between them. It's the square of the distance between them, so you have to put a square on it. Here we have Newton's law of gravitation, and that's really what it looks like. Newton's law of gravitation. Mr. Apple on his head, this is what he came up with. So I guess we just did part A. Write Newton's law of gravity as a formula. Boom. According to a physics experiment, we got some numbers to play with here, right? So what are we going to do with these numbers? We're going to solve for k. That's what we've always been doing, right? Is saying, okay, well, there's the general law. So what's this constant of proportionality k then? Well, take some numbers and plug them in. F is 50. Fine. And I'm not giving units because units don't matter as long as you keep your units the same every single time. That's all that matters. But anyway, when M1 is 80 whatevers and M2 is 40 whatevers, okay, cool. And it says R. I guess I meant D for distance between them. The distance between them is, what? 2. No, 2. Yeah, 2. But don't forget the 2 is squared. Okay, so it's like a 2 squared. So I guess we did it. We plugged in all our numbers, right? So let me make sure I did this right. F is 50. Yep. M1 is 80. M2 is 40. R is 2. Yep. We did it. Good. Of course, now we have to solve this thing for k. So what do you say we start doing things like this? 80 times 40. Well, 8 times 4 is 32. Put a couple zeros on it. 2 squared is 4. Okay. Well, I can divide the 3200 by 4 right now. 3200 by 4 is 800. Okay. So you just kind of do one step at a time, and the exact path that you take might be different from the exact path that I take. Doesn't matter. As long as we do legal moves every step, we'll be fine. 50 over 800, what's that? Well, I can cancel some 10s right there. 5 over 80 will reduce to 1/16th. Or if you want, we can get all decimally about it. 0.0625. So, Newton's law of gravitation is force equals the k. We just solved for the k in our lab. 0.0625. Times the mass of object 1 times the mass of object 2 and divided by the, whoops, I was using a d, wasn't I? By the distance between them, but the distance has to be squared. Please note that that's just a subscript. It's not telling you to do anything with your calculator. It's just a label. It's like a piece of tape that says this is mass number 1 and this is mass number 2. Whereas d squared, well, that's an exponent, of course. You have to actually push an exponent button on your calculator. Anyway, there's our law of gravitation. What was the question here? Oh, so we're going to do this. Accordingly, solve for the constant proportionality. That's what we just did. Fine. Next. M1 is tripled, but the distance between the objects is also tripled. How does the force change? M1 was tripled, huh? Well, what was M1? M1 was 80. So we're going to triple that. I'm going to say M1 is 3 times 80. I'll just write it out so we can follow what's going on. So M1 is going to become 240. M2 doesn't change, I don't think. They didn't say to change M2. Nope, they didn't. So M2 is going to, I'm going to say stays at 40. But the distance between them also triples. So it used to be 2, didn't it? Distance used to be 2, but they're saying the distance is tripled. Okay, so the distance is going to be tripled, so it's going to be 3 times 2. The distance is going to become 6. So I'm using a 240, a 40, and a 6 now. So what's my new force of gravitational attraction? Take your 0.0625, multiply it by M1, which is now 240, multiply it by M2, which is now, what, 40, and divide it by D. Remember, squared. So by 6 squared, that's an F, by the way. And this is just pushing buttons on your calculator. So what am I doing? I'm typing 0.0625 times 240 times 40 divided by, and I'm just going to type in a 36 because I know that 6 squared is 36. So dividing by 36, and I got boom. I got 16, like 0.7-ish if you round. 16.7 is the new force. So, out of curiosity, what was the old force? The old force was 50? Really? The old force was 50. Now, if you make an object heavier, it will have more gravitational force, right? But we went down. Why did we go down? It's because we spread them out much further. So the further you are away from something, the less the force of attraction is going to be. It's kind of like if you go up into space, you'll be weightless, right? So it turns out that tripling the distance really kind of had the biggest effect there. And so instead of a force of 50, we have a force of 16.7. Okay, well, there it is. That's all the variation talk. Again, it's mostly a matter of being able to take when somebody says something like this. The force of gravitational attraction between two bodies varies directly with the masses of the two bodies and inversely with the square of the distance between them. That you can take a sentence like that and you can say, oh, they're just trying to give me a formula here. The formula is going to have some constant of proportionality in it that you have to solve for. So you need some kind of data in order to solve for that k. But once you've got the k, you then have a full-fledged formula that you can use to analyze for whatever new situation you want to play around with. Okay, so this is kind of like a unit unto itself. It's, hey, here's how you read your science books and your technology books and stuff like that. So hopefully it was kind of enjoyable. I can dig it.